somewhere on the internet forever. And I think, hello. All right. So Thomas, you're good to go.
Okay, thank you very much. Well, thanks a lot for the invitation. As I already briefly mentioned, it was also briefly mentioned, Varro. Well, I'm actually a physicist, and so this is really my first time talking not to mathematicians or giving a talk to mathematicians, but making really a talk with like proper theorems and also discussing some proofs. And the reason for this is that we recently completed a paper with three brilliant mathematicians, Ben Bakker, Christian Schnell, and Jakob Zimmermann. So Zimmermann is in Canada, and Christian is in Stony Brook, and in Chicago is Ben Bakker. And much of the talk will be based on this paper, and in the very end of the talk I will mention some follow-up where I essentially made a courageous conjecture kind of out of the experience with this mathematical paper. Okay, so let's get started. So the very first part of the talk will be a bit more physicsy in spirit. So it will also be a bit more rough, but I hope you at least get the idea where this finiteness theorem comes from, or why are we interested in this finiteness theorem from a physics point of view. And so I will start very general. So what are the kind of the cornerstones of like fundamental physics? Like if you want to understand all laws of nature, we have to check what do we know already and kind of how to combine these laws. And so one piece of theoretical physics is essentially the standard model of particle physics. It uses a special quantum field theory. Yeah, it talks about matter, particles, and interactions, and so on. And mathematically, from the tools, it's like using aspects of analysis. And on the other big theory is describing cosmology and the force of gravity. And this is Einstein's theory of general relativity. And it uses Riemannian geometry, as you surely have heard about. Yeah. So in this part, it's more about manifolds and differential geometry. And now the big question, which we are thinking about, and there are many people working in this direction, of course, is how to combine these two theories, right? And this is a very tricky thing. And what the outcome of such a combination would be is a theory of quantum gravity. So how to quantize gravity and combine it with the standard model of particle physics. Now, string theory is a promising candidate theory which achieves this. Yeah? And it has been studied over many years. Maybe it started in the 80s, so it's quite a few years already. And leads to kind of many exciting connections also with mathematics, as you will see. Now, what is a recent development? A recent development is some sort of a shift in perspective, and it's a kind of a very broad research program which emerged, which is called Swampland Program. It's a bit of a strange name, but mathematicians are used to giving strange names. So the Swampland Program is essentially promoting the idea to identify four-dimensional models, which are four-dimensional physical theories, if you want, which are compatible with quantum gravity, and understand what are the features of these theories which make them compatible with quantum gravity. Yeah.
So is this for real or for complex dimensions?
This is for real. So this is our world, our four-dimensional world. So you make a model for our universe, and you ask if this model of our universe can possibly be consistent with quantum gravity. Yeah.
And in complex is not real.
Yeah, okay. So the question then is the following idea. So you have this set of models which you can cook up, right? And the idea is that from quantum gravity point of view, only some of them are actually consistent. And you might not see immediately the reason why this is the case.
So when you write quantum gravity string theory, there's one name?
Yeah, so here...
Is that one subject or is this...
Yeah, so the issue is a little bit, of course, people are more courageous, so they study things in string theory and then claim that it is true for all theories of quantum gravity, which you could imagine. Now, it could be that string theory is the only one which is consistent, then these two things are equivalent. But one doesn't have to make this assumption. Yeah. Okay, so this is a broad field, and there are many people working on this. And we have a conference coming up here in Utrecht, Things in Geometry, and you will see some of the top speakers like Komon Wafa coming and giving a talk here. Okay, so this is this is field, and so why does string theory yield many four-dimensional models, and what has this to do with geometry? Right, that's what the talk is about. Well. The reason is relatively simple. If you realize that string theory is actually formulated in higher dimensions, in 10 space-time dimensions, so 10 real dimensions, and there is actually a version which is called F-theory, which is a 12-dimensional theory. I just encourage you to remember, that we are talking about a 12-dimensional theory, that you see how the dimensions add up. Now, so what is the idea to get our four-dimensional universe out of this 12-dimensional or 10-dimensional theory? Well, we take the space-time background to be a product of two spaces. So one is our four-dimensional universe, which is very large and we can see every dimension. And the remaining 6 or 8 dimensions are to be a compact manifold. Yeah. And now, because this is a compact manifold, and we are in very high dimensions, there are many choices for these compact manifolds. Yeah. And these many choices imply that there are also many choices of possible universes, if you want, in the other four dimensions.
And why compact?
So the compactness is very important because this translates gravity, so the force of gravity which you have in this higher dimensional theory, the compactness allows you to translate this force of gravity into the four-dimensional theory. If you would give up compactness, then gravity could somehow be diluted over the non-compact directions. And then you wouldn't see a four-dimensional gravity theory. So in theories of holography, for example, you don't need this compactness necessarily. But since we want to test kind of quantum gravity from a four-dimensional point of view, compactness is very important, and you will see, it's a good question, that this compactness is very important for this finiteness theorem as well. So, in any case, the four-dimensional physics depends on the choice of this manifold. Now, there is a problem with this picture, which is immediate, that kind of the deformations of this space correspond to massless fields. So if you imagine your compact manifold, imagine some torus, then you can change its shape, which would be its complex structure. And from a physics point of view, this kind of deformation would be really bad experimentally. It would be a fifth kind of a new force if it is massless, and it would be in immediate contradiction with experiment. So what you want is, you don't want these deformations of these manifolds to be kind of unfixed. We want to kind of abstract them, yeah, in a mathematical sense. And the solution for this has been suggested some time ago, namely in around 2000, and this goes under the name of flux compactifications. So let me explain in a few words what flux compactifications are. What is the rough idea? Now you imagine that you have your compact manifold. I have drawn a figure here. That's our compact manifold. And I choose it to be 8-dimensional, right? So 8 plus 4 is equals to 12. So 8 real dimensional manifold. And then I switch on something like an electromagnetic field on this manifold. And it's a kind of a generalization thereof. So it's actually not a 2-form, which would be for an electromagnetic field, but it's a 4-form. So it's a 4-form on an 8-dimensional manifold. So it's half-dimensional form of a manifold. Okay, so that's how you can envision it, and it will be a differential 4-form, and this form will be called flux. It's just a name. Yeah. In fact, the equations of motion, something like the Maxwell equation, which follow from this string setting, imply that this form actually has to be a form in this Chromology group. So the relevant information in this form is actually in this Chromology group. So you should think of it as a class in this Chromology group.
May I ask a question?
Yes.
So, here you're talking about 8-dimensional Y, but if you take a 6-dimensional and restrict to Calabi-Yau, then the condition is that it's a rigid Calabi-Yau.
Yeah, this is something which you could also do, yes. Yeah.
Yeah, but an analog for deformations, you do not want deformations. Not at all.
Yeah, but what we do is we kind of, this is what I will explain now, we will fix these deformations using this form.
Okay,
So
may I ask? So these Calabi-Yaus, you can give us a definition. You can also give some example equations. Do we have example equations for this 8-dimensional one?
oh yeah, these are 4-dimensional Calabi-Yaus, Calabi-Yau 4-folds. I will come to this in a moment. Yeah.
Okay.
So it's exactly what you're thinking about.
Okay, then
Yeah. I just started a bit more general like that.
Yeah.
Okay, so now then, in fact, there is a quantization condition on this flux, and this quantization condition actually implies that this form is not just kind of in the cohomology over R, but it's actually an integral cohomology. Yeah, so it's really some kind of quantized object living on this manifold. Yeah. Very good. Now, if Y is compact, which, as I mentioned and was asked, is relevant for gravity, then we know from a physics thinking that there are some consistency conditions. So now take a compact manifold and you put some positive and negative charges on it, and then, well, there's charge conservation, and so you have to put as many positive as negative charges on this manifold. And now, it's equally true if you switch on this kind of 4-form, this integral 4-form, and then this charge conservation condition actually adds to this equation, namely this 4-form introduces some charge, and then I can add positive and negative charges, and they all have to add up to 0. Okay? And this can be rewritten in the following form, namely that the self-intersection number of this 4-form actually has to be some integer L. Okay? So now I wanted to discuss kind of what is then the solution to this problem of this kind of deformation problem. And it is the following thing which has been found, namely that this 12-dimensional theory admits, when you solve the Einstein equation, the following solutions, namely that the 12-dimensional manifold is a product. There's some details which are not too important, it has to be warped, but that this Y is actually a Calabi-Yau manifold. Calabi-Yau fourfold. Yeah? And it is a Kähler manifold with vanishing first Chern class. Yeah? There is a similar story, by the way, for Calabi-Yau threefolds, and in our paper you will also find theorems which can be applied to Calabi-Yau threefolds. Now, then there is this four-form flux, which is an integral flux, and it satisfies this condition for the intersection. Now, the equations of motion, Einstein's equation and the equations of motions of the other field actually imply two conditions on this flux. Namely, that when I apply the Hodge star operator on this differential form, it has to go back to itself. Yeah? So now I hope that every one of you has seen the Hodge star operator from differential geometry, and it's in the middle cohomology of this manifold, and it has to go back to itself. And it has to be primitive, so it has to wedge with the Kähler form to 0. Yeah? And now this is what we would call a self-dual flux. Why do I call this self-dual? Well, because the star on the flux goes back to the flux itself. Now, and this you should now read as a condition on the choice of the complex structure and the Kähler structure. And this is what fixes your deformations. Because if you look at these equations, they are not invariant if you change the complex structure of the manifold. Yeah. And here, this is not invariant if you change the Kähler structure of the manifold. And this is the idea of fixing these deformations. So now the problem is my clock is gone.
So it is 20 past almost.
Okay.
So 20.
So now the question is, there was a concrete conjecture which was appearing shortly after these kind of settings were found. Namely, the question is, how many such solutions to these equations do exist? So how many choices of G4, these integral classes of flux, can you find which satisfy these conditions? And what we now have proved in this paper in much more generality than in this Calabi-Yau setting. It's abstract, it's much more abstract, as you will see. And also Calabi-Yau-ness is not really central there. But if you apply it to a Calabi-Yau configurations, then you find the answer is actually yes. There are only finitely many solutions. And the physicists, of course, they are more courageous. They even want finiteness of choices of these manifolds, and then you would need the finiteness of compact Calabi-Yau manifold. And this has not been proved so far. But people believe it's true, and it would be very exciting to make progress on this.
But, so G4 was the Chromology class, the four-dimensional Chromology class, or you also think about the form?
About the classes, we think about Chromology. Yes. Yeah, it will become more mathematical in a moment, but it's just that
confused by finitely many choices for a model. You make this finite dimensional. No, it's not used.
No, really finitely many integral classes.
Okay.
So what do you mean by finiteness of Calabi-Yau manifolds?
So that they are finitely.
You must identify certain things.
Exactly, right. So you have to use something like Wall's theorem to kind of attach to these manifolds some topological invariants, and then you say there are finitely many choices for these topological invariants.
So these could be the Hodge numbers.
These could be the Hodge numbers, for example, but it's not enough. So you need the Hodge numbers and the intersection numbers and chain class.
Okay.
And it would be exciting. It would be very exciting to prove something like this, but currently this is out of reach.
And what's happening in dimension 4 when you're talking about K3 surfaces? How many K3 surfaces do you have?
Yeah, so there it's already clear.
No, it's not clear to me because I understand the information of K3 surfaces.
True, but really as topological classes there.
Okay, it's topological physical.
Okay, very good. So now, of course, as physicists, we are much more courageous because we don't need to prove things exactly. So one can turn this into a much broader conjecture and ask if these number of four-dimensional models is actually finite. Yeah? And that's what people have studied over the years, and there's a lot of exciting progress, and it's part of the swampland program now. Okay. Now, what I did here in this paper is actually to say, well, this finiteness criterion might be boring if this is just a yes or no answer. So if you say, is it finite, yes or no, then it's just a boring kind of statement. However, maybe this finiteness is actually a new structural principle which we should use in order to understand our theories. And that's exactly what I suggested last year, and it came from the proof of this theorem. In fact, it will use this Tame topology, and I essentially made a conjecture that this Tame geometry underlies essentially all consistent physical systems. Okay, now let's go to a more mathematical formulation of the problem, and hopefully then some of these questions are resolved. So Calabi-Yau manifolds, we start with some Calabi-Yau manifolds of dimension d. So I need to put my clock here, otherwise I run hopelessly over time. Okay, so Calabi-Yau manifolds of dimension d. Well, they are scalar and have the first Chern class vanishing, and then Yau's theorem tells us that they are Ricci flat, and we can find a certain scalar. We can find a certain Ricci flat scalar metric with certain properties. Okay, and then what do I mean by deformations of the manifold? I mean by deformations that I can now deform the complex structure of this manifold while preserving the Calabi-Yau condition. And you can think of this as preserving the Ricci flatness of the metric. Now what you can do is you can check how many such deformations exist, and you can show that there exists in fact an HD minus 1, d dimensional unobstructed moduli space describing these deformations. And then, in fact, you should not think of this manifold as a single manifold, but actually as a family of manifolds changing over this complex structure moduli space. So the complex structure moduli space, a simple local model would be a punctured disk, and then your manifold changes when you move over this disk. And for example, when you come close to the puncture, it can even become singular. And one can now show that this moduli space is quasi-projective and that it can be made smooth. Okay? Now, why is this important? Well, the Hodge star which appeared in the self-duality condition actually changes over this moduli space. And to capture this change, what we now do is we introduce a PQ decomposition of the Chromology. It's a scalar manifold, so we can do that. A Hodge decomposition, and for our Calabi-Yau fourfold, or for our four-dimensional complex scalar manifold, we find this decomposition. And now we can check what happens with the Hodge star, or if you evaluate the Hodge star in Chromology, that would be called the Weil operator. And the Weil operator would act with +1 on this piece, with -1 on this piece, with +1 on this piece, and so on. Right? So there's a concrete match between the PQ decomposition and these operators. So what are now these self-dual solutions? Now you can write down what that means mathematically. That means that this G4 is actually a class, yeah, in this space, in the integral cohomology, and then this part here, and I suppress the primitivity. There's some primitivity conditions. Okay, and so these fluxes are allowed by this self-duality condition. And now the finiteness question goes from studying the change of the Hodge star to studying the change of the PQ decomposition over the moduli space. And this is what is called the variations of Hodge structure. So how do the Hodge structure vary over the manifold? Now, So why is this finiteness question non-trivial? So at first you might think this finiteness question is absolutely trivial. Okay, why would you think that? Well, let us consider a fixed PQ decomposition, right? Then I introduce what one calls a polarization. It's some bilinear form on this Hodge decomposition, and for all practical purposes, which we in this geometric setting is just a wedge product between two forms, right? Two four forms on this Calabi-Yau form. Well, if I do that, then this kind of constraint that G4 wedge G4 is equal to L, and self-dual implies this equation. But this is just a positive norm, and this has to be equal to L. So then you can think of this as like a circle with a fixed, or a kind of a sphere with a fixed radius, and then you have to count how many integral points are on the sphere. And it's pretty obvious that once you fix the radius of the sphere, this has to be finite. Yeah. So there, it's a triviality. However, we said that we want to allow for the variation of the Hodge structure, of the variation of the PQ decomposition, and this turns this into a very hard mathematical problem. And why is that the case? Well, because if I change the Hodge structure, this kind of the radius, kind of this norm, how I measure the size of this circle or the sphere, changes when you move over the moduli space. And we know that the while operator actually degenerates near the boundaries. So this can be arbitrarily large near the boundaries. And so you could think, oh, but that means that there are infinitely points for sure on this sphere. And so now one has to carefully check that this does not happen. So you have to check that these infinite tails in the asymptotic regions of atoms actually are not there. Right? And you can never pick up infinitely many such integral classes if you go to the boundaries of the space. So now how did I end up with this question anyway? So what we actually did is we used some of the techniques of asymptotic Hodge theory, which exactly asks what happens with the PQ decomposition if you go to the boundaries of the moduli space. And we applied them to some of the swampland conjectures. And so it felt completely natural to use these techniques to prove this finiteness. And in fact, it turns out in one parameter limits that works pretty well. So you have to use both the nilpotent orbit theorem, the SL2 orbit theorem in one variable, and then you can prove the finiteness of these integral classes, self-dual integral. And you really need the full power of these theorems. It's quite remarkable. However, if you want to go to multiple higher dimensional moduli spaces, it's just too complicated. So this multivariable SL2 orbit theorem is really complicated. It's really nasty. In fact, it's hard to explain this in such a short time, but just kind of to give an indication. So this paper appeared in 1973, and this paper appeared in 1986. So it took the people these mathematicians to go from one variable to n variables about 13 years. Of course, that doesn't mean much once you understand it, but still you can at least a little bit imagine where this complication comes from. So now let me state kind of this finite statement, this finiteness statement in a really proper mathematical fashion, namely as theorems in abstract variations of Hodge structure.
So what are these limits in your moduli space when they become very singular?
Yes. So these limits in moduli space are precisely the degeneration limits of these manifolds, and they can be arbitrarily wild. So maybe some things which you know well is kind of there can be like a 4-cycle shrinking to a point. So at least like a conifold or 3-cycle, like a conifold point. But there are much more wild things like the where you kind of break up this manifold in many pieces. So
Even for sextic Calabi-Yau fourfolds, you already see all these different.
it all applies there, and for the sextic you would have some sort of analog of conifold point there, but you also have this point of maximal unipotency, and this is the wildest point of degeneration, if you want, which means, anyway, let's not go off track here, but yeah, indeed. So, and what you have to do is you have to make sure that when your manifold kind of splits up and degenerates mildly, that in this process, going closer, that you cannot get infinitely integral classes on these manifolds if you go closer and closer. So there is some very non-trivial structure which kind of prevents this from happening. Okay, so now what is I wanted to quote a famous theorem which one might want to use for this, and that's also where I kind of started off with, and this is the following theorem. Let's now take x to be a smooth complex algebraic variety, namely our moduli space. You can think of this as our moduli space. And then we studied the Hodge bundle. That's just what I said, this kind of changing PQ decompositions, and then there are some rules how to glue it together. There will be some connection on this and so on. And I demand that P plus Q adds up to 2D. So for the Calabi-Yau fourfold and the four forms, this D would be 2. Right? So I look at even weight Hodge structures. And then there is this famous theorem by Catani, Delin, and Kaplan from 1995, which almost looks like what we need. Right? It states the following. If I look at a positive integer and look at the locus of integral Hodge classes, namely of X and V element this Hodge bundle, where V satisfies that it's kind of type D, D, and it's integral. Yeah? And that Q of V, V is equal to L. So this was the condition which we motivated charge conservation. Yeah? And this is the integrality condition, and then we have also element of HDD. So this is a remarkable theorem. Why is it remarkable? Because the same statement follows, with some caveats, from the Hodge conjecture. And it's often quoted as kind of the strongest evidence for the Hodge conjecture. So the Hodge conjecture, as you know, is this like big open conjecture where when there's no good approach to it. So every piece of evidence is exciting, so to say. Yeah, and in fact, this theorem can be viewed in this way. So there's a famous big theorem. So it would be very nice if this just covers our finiteness result. Did I say what this theorem is? So we have this locus, and then this locus is algebraic. So this locus where X and V satisfy these conditions is algebraic. Yeah? And that means it has finite components. Yeah? And that would be an immediate proof of what we need. It has also, the projection map has finite fibers, but I already explained to you that this kind of feature is trivial, right? That when I look at a certain fiber, then it's finite. So the question is, what happens if I look at all the finite fibers? Is there a uniform bound on this finite number?
So what does algebraic mean? What thing is algebraic in this?
So algebraic means that this set can be described by some algebraic equation in this boundary.
This is an analytic condition.
No, QVV is added in algebraic condition.
But
Oh yeah, but this is a highly non-algebraic starting point. You have to imagine that you have all these period integrals there which have exponentials, and the statement of the theorem is they all magically cancel if you look into these Hodge classes.
Okay.
So it's a remarkable statement. And how did they prove this? They exactly proved it with the SL2 orbit theorem. So they actually went through the whole theorem and used all the details, well, most of the details there, but they also used holomorphicity. So this covers.
But the hard part is being algebraic or the finite? Well, no.
Yeah, so these both parts have non-trivial parts to it. Yes. So the finiteness is non-trivial, and also the algebraicity is non-trivial. And what we will see, we generalize the finiteness, but what is the exact statement for the algebraicity? That's something which is still open. Okay. So this covers the finiteness of the special case where G4 is actually a 2-2 form. But I told you we can also have 4-0 and 0-4. And this is just not covered by the theorem. Okay, so this is now the theorem which arose out of this work from these mathematicians. Of course, I should get a mild credit on this. And so what is the statement? That if I introduce now this Hodge operator, this Hodge star or this while operator, which acts on these classes of HPQ as this, then I can introduce the following set, right? We look at integral classes which are self-dual and have a fixed self-intersection number here, or self-product to be equal to L. And then the statement is that this set is not algebraic. It's actually, we know it's not algebraic, complex algebraic, and also not real algebraic. But we know that it has a certain structure which is called, it's R and X definable. Yeah? And as we discuss in a moment, this also implies finiteness. So while it's weaker than algebraicity, we still have a finiteness theorem. And now, just to kind of recall the information, this is exactly the statement that we have a quantized flux. This is the statement we have a self-dual form, and this is the statement that we have charge conservation. Okay? Now, to understand the theory now, I should give you a brief introduction to Tame geometry. And the first thing is, so why do I do that? So we want to use, later on, we want to use some recent exciting theorems which connect the study of Hodge structures to this Tame geometry. Yeah. And the statement in the final theorem which I presented will be understood only in this notion of Tame geometry. So it's actually kind of deeply linked to ideas of logic. Okay? And the remarkable thing is that this connection came up. Okay, so where does this come from? Well, okay. To what does this relate? I wouldn't say it comes from this, but it relates to this. Namely, in Grothendieck's, he published a sketch of a program. It was apparently a grand proposal, where he kind of laid out an idea of inventing a topology which is more suitable for geometers, yeah? Rather than for mathematicians doing an analysis. Okay? And essentially he said, well, we want to remove pathologies that occur in ordinary topologies, like Cantor sets and all these things. Okay? And this is what he called a tame topology. And then he sketched some ideas. What should be the features of this Tame topology? Now, what happened in logic is that mathematicians in this field developed the the topic of O-minimal structures, and as kind of part of model theory. Okay, so this comes from logic, and in fact, these O-minimal structures can be used to construct such a Tame topology. And this Tame topology is a generalization of real algebraic geometry. And in some sense, you see already why we need it, because, as I told you, these kind of subsets are not anymore algebraic. So we need something going beyond algebraic geometries. And also, the PQ decomposition, this periods or this change of PQ decomposition, is not algebraic. So that you need something fancier, but which has still some nice properties. And what is the basic idea? The basic idea is to specify a set of allowed sets of Rn, which we call definable sets, and allowed functions, which we call definable functions. Okay? And once you have sets and functions, you can define what you might mean by definable manifolds or definable bundles, and then you can construct a whole Tame geometry. And what is so exciting about this is that this whole construction has strong finiteness properties. So finiteness is kind of automatically built in. Now, I should now explain you a little bit how is it built in, okay? In these few minutes, but I will try my best. Okay, so the simple situation you could imagine is look at the real line and ask what are kind of sets of subsets. How would I implement finiteness? Okay. Well, if I just look at individual points, then finiteness just means I have finitely many points. Yeah. If I look at intervals, well, an interval has infinitely many points. But I just don't want to count them individually. I want to count them as one interval. So I just allow finitely many intervals. And these intervals they don't have to be of finite length. I don't want to have just things which are compact, right? I also allow things which stretch to infinity. And this then gives you open intervals. And these are the sort of finite sets which I allow in this Tame topology. Now, this is of R, so that we can visualize what is the natural thing to do. The tricky part is, how would you extend this to Rn? Yeah. And in some sense, and this has a clear counterpart in logic, in some sense the most important condition is that every projection through a higher dimensional set, every linear projection to the line, has to always lead one of these. And that's how you kind of restrict your higher dimensional sets. So whenever you project down, at the end of the day, if you end up in one dimension, it has to be one of these sets. Okay? And then now you can imagine that this gives you a lot of restrictions on what is possible. Of course, you also want to make it closed under finite unions, intersections, products, and so on. It should also be an extension of algebraic geometry, so we include all sets which are solutions to polynomial equations. Yeah. Of course, these things are compatible. Yeah. So if you have a polynomial equation, which has point solution, that's just finitely many solutions.
So,
and this
those people also often use inequalities.
Yes.
Positive and so on.
Right.
Is that
This comes exactly from the projection.
Okay.
So indeed, it's not just the algebraic sets, but it's the semi-algebraic sets.
Okay.
So you need the inequalities. Okay, so now I give you the formal definition of the O-minimal structure. So these are the subsets of Rn, which are finite unions and so on, which I mentioned already, the zero sets of every polynomial, and the tameness condition, and this is the only tameness assumption in this setting, is that when you project it down to the one-dimensional case, or not project, but if you look at the one-dimensional sets, then you find unions of intervals and points. And that tames the whole structure. This information kind of carries over to the higher dimension structures. And then you can introduce definable functions, are those whose graph is part of the mononomial structure. And then, just to give you some example, every polynomial function is a tame function by definition, because I told you that every algebraic set is part of the structure. But there are easy non-examples. So the sine function, a function which we love, yeah, to some extent, on the real line, is not part of the structure, right? Why is it not part of the structure? Well, you can project along this line here, and then it has infinitely many zeros. And infinite discrete sets are the killer for Tame topology. So infinite discrete sets are never part of Tame topology. Now remember, we were talking a lot about lattices before, like integral classes. So how do these two things come together? And that's kind of the exciting part of finiteness. Okay, and then you can have definable manifolds which have finite atlas and transitions functions which are definable. Now let me
So
just
this will be compact.
say again.
No, this will not be compact. This may be compact.
Oh no, yeah. No. Compactness is actually not a good condition. Would be also bad because all these moduli spaces are not compact. Okay, so just to give you one more flavor on this. So now you can prove theorems within these structures, and one of the famous basic theorems is that if you have such a definable function in some O-minimal structure, then you can prove that if it is a map from R to R, that you can always split R into finite number of intervals, and F is either constant or monotonic and continuous on these intervals. Yeah? And it can jump at finitely many spaces. It doesn't have to be continuous over the whole line, but it can only jump at finitely many places. And the second result is if you have a definable and holomorphic function, then it's actually algebraic. So you see it's a very strong condition, right? So that means that a holomorphic function would be like an infinite sum of terms, but if you require definability on C, on the whole complex plane, then it can only be a polynomial. It's a strong condition if you have the whole thing. Okay, so now if you do that, you see that the complex exponential is never definable in any O-minimal structure. So if you go from C to C, the complex exponential is never definable. So that sounds like a complete killer for every application, but it's actually not. The remarkable thing is that what one finds in these Hodge structures is not complex exponential valued on the complex plane, but it actually, there is a bound on kind of the angle in the complex structure, in this set. So why is it not definable? Well, if you write the complex exponential like this, you see that the cosine and the sine appears, and I told you already, they are never definable. Yeah. So now it seems like if you restrict the domain of this angle phi here, you made it definable, but it can only be definable if e to the r, the real exponential, is also definable. So it has to be a definable function. And the question is, does such an O-minimal structure exist? And this is non-trivial, this is very non-trivial. Namely, there is no unique O-minimal structure, there are many such structures, and to construct them is a challenging task, right? Because you want to have it closed under all these axioms, and you want to make sure that when you project down to one dimension, it's kind of always in these finite sets. And to prove this can be extremely non-trivial. And I want to give you some examples. One example is the easiest example is the structure generated by the real polynomials. Yeah? And this is called R-alg. And the structure the sets which generate this structure are just equations of this type, namely the one which have equal to 0. But because of this projection identity, you actually find that all the unequal sets, like where this is unequal signs, will also be induced automatically. And so this is actually the set of semi-algebraic sets. Now, that's not too exciting. The exciting part of the story is actually to make the structure bigger without violating the O-minimality condition. And that's very subtle. And one way of making it bigger without violating O-minimality is to add restricted analytic functions, which are functions which are analytic on some ball, and then you restrict it to a ball which is slightly smaller. And then you add these functions in all of these balls, in all possible analytic functions. And this set of functions is still O-minimal. But probably the most remarkable thing is, because this doesn't have this kind of any compactness statement or restrictedness statement in there, is that you can also add the exponential function to this. And you can generate an O-minimal structure by looking at all the sets which have just polynomial entries and also the exponential function appearing. And this is apparently a very deep theorem in logic, which guarantees that this structure generated by the sets is still O-minimal. And it's proved entirely using logic machinery. Of course, logism also translated into geometry first. Maybe some of the experts are here, so I'm not claiming that I understand the proof of this theory. Okay. And then now you can combine the two things and you will still preserve O-minimality. So you can look at the restricted analytic and the exponential functions, and then this gives you this thing. And in fact, in order to understand the definability of e to the z, the complex exponential, you already need this. You already need this O-minimal structure. Why? Well, we have seen it already, right? We need for the cosine and sine, these are analytic functions, and if you restrict the angle, then it's a restricted analytic function. And you need the exponential because it's an exponential, a real exponential part. And in fact, it turns out that this is sufficient for most geometric applications. But I should mention that there are also functions which are not definable in this structure, namely the gamma function, the error function, and the zeta function are just examples. But these are not crazy functions, right? I should say. But they are not definable in this structure. And they appear in physics all over the place. But the remarkable thing is they always seem to appear in such a way that this kind of bad non-definability cancels. That's what we are now seeing more and more. Now, this is not the end of the story. There are many deep results on this, and many of these deep results are based on the existence of what is called a cell decomposition. So there are always kind of finitely many cells to decompose your sets. And just to kind of give you some names of some theorems, so there's a kind of a definable version of the Chow theorem, where compactness is replaced by definability. And then there are interesting counting theorems which are used in many of these deep recent proofs, like also when the Andre-Oort conjecture was proved recently. This is always using as, well, first of all, it's using this O-minimality story, but it also crucially uses these counting theorems. So many of these finiteness theorems use them. Okay, now I'm running a little bit late, so I can only sketch the proof briefly. Of course, it's a lengthy proof, and it uses many of these recent developments. But maybe I can sketch a few main steps. Okay, please be patient through this part. Well, okay, you're a mathematician. You're used to this. So we want to use the definability of this recent seminal paper by Baker, Klingler, and Zimmermann, 2018, which kind of proved the definability of maps which appear in Hodge theory. So in particular, let's look at the while operator and view it as a map from this X, right, which was the base, our moduli space, to this quotient of groups. And G is the orthogonal group of Q, and K is the orthogonal group of this Q fixed at some C0, some while operators. And you can understand every while operator as such a map. Okay? And then a theorem which is proved in this paper is that the while operator map is definable in R and X. And in fact, what this does is it uses this nilpotent orbit theorem. It uses one of these asymptotic Hodge theorems. And okay. So the reason why this can be done is everything which is like on compact sets can be shown rather easily because the restricted analytic class is very large. But if things are non-compact, so if you go to the boundaries of the moduli space, there the hard work begins. And you have to use monodromy and these like local Hodge theory considerations. And this was done in this paper, leading to this result. I'm not sure if it's stated there exactly like this. Now, that's kind of, in some senses, a little bit the easier part of the story. It just crucially uses the nilpotent orbit theorem, but the more difficult part of this paper is actually that they show that even if you quotient out the integral lattice, so even if you quotient out the integral lattice coming from the orthogonal group of this restricted to the integers, even if you do this quotient, it's still in Rnx definable. And this should not surprise you that this is difficult, because this is a lattice, right? So this is kind of an infinite discrete thing, and definability is usually not preserved under doing things with an infinite discrete group. Yeah. So that there must be something non-trivial going on here, and in fact, that's the tough part. And the way how one does that is essentially one has to introduce something which is called a Siegel sets on these quotients, and then you have to always show that such maps always end up in a finite number of Siegel sets. You have to introduce a finite atlas of this, a definable structure of these quotients, and then show that this while operator or the period map actually maps only into finitely many such Siegel sets. And this is of course involved, and if you're interested, I looked into this a lot, so I'm happy to discuss this further. Now what we did is we now extended this to this Hodge bundle, kind of by multiplying with this vector bundle here, with HC, and showed still definability there. And then we show, then the idea is to show that the locus of self-dual classes in this image here is actually R-alg definable. Yeah? And then I can use the definability of this map to pull this information to the Hodge bundle, but since this map is definable, definability is preserved. So if I show that this set is definable here, and the pre-image of a definable map is definable, then I can show that the set here on the Hodge bundle is also definable. And that was precisely the statement of the theorem. Okay, and what is the trick behind this? So it goes a little bit of lattice theory goes into it, which is quite exciting. Namely, you really need this condition here. If you have this condition, then you can show that this group gamma, which was this whole integer orthogonal group, reduces into finitely many orbits. Yeah? So this can be found in Kneser's book, for example. No? And so, so that goes precisely to the question which was asked before. Compactness is very important of the manifold because compactness implied this condition of charge conservation. And this compactness actually is the reason why we have finiteness. If you drop this condition, then you can have infinite tails. Okay? And finally, then you have to show that in a single orbit, in a single orbit, you get for self-dual classes, you get a definable set. And this is a little bit of computation, and then another deep result from this paper, namely that the maps between these arithmetic quotients are actually definable. Okay, I realize that I cannot explain this in five minutes, but if you want to discuss this further, I'm of course happy to. So this brings me to the end. So this is kind of the proof, and if you put all these pieces together, you get exactly the statement that I gave before. And motivated by this success, what I did is I kind of, on a more physicsy ground, I did the step which I explained before as well. There was this finiteness conjecture for these solutions. And now you can ask, is there maybe a finiteness or a tameness statement for all of these models which come from quantum gravity? And this is what I formulated in a conjecture, namely that all these models from quantum gravity are actually, you can describe them by using tame geometry. Yeah? And so if you want to keep like since you're not physicists, maybe this doesn't, it's anyway fine to state it like this. So all consistent physical theories are tame. That would be the punchline out of this conjecture. Whether or not this is true remains to be shown, and I think it's an exciting thing which we are looking at the moment. This brings me to my conclusions. So this Swampland program addresses exciting questions at the interface of physics and mathematics. Yeah, so that it's not only me who works rather mathematical, but there are quite a few people really working on the interface, and it would be very nice to bring the two fields or two institutes, if you want, here in Utrecht together, and on these topics. And this mathematical approach actually allows us to settle long-standing conjectures, right? So you can see this also as a proof of principle, right? So we can actually prove something, and it can excite also the physics community. Of course, it excited the person very much who made the conjecture, Mike Douglas, so he was happy that this progress is made. And now tame geometry and omnimal structures could actually play a useful role in string theory settings. So I remember there was a master student coming to me, or bachelor student, asking if I have some project in logic for him. And I said, well, I have a lot of projects in all kinds of fields. String theory relates to everything, but I didn't have a logic project. So the exciting thing is somehow that there is now even some kind of deep connection to these kind of structures which arise from logic. And then you can ask how it relates to other conjectures, and also maybe quantum field theory itself is tame. Okay, thanks for listening. Sorry for running over time.
Are there questions in the room?
Yeah, can I ask, so in your main results, there at some point you didn't need Calabi-4 anymore.
Yes.
So can you repeat again what's very special about Calabi-4?
Yeah, so in abstract variations of Hodge structure, you just study how a Hodge in HPQ decomposition varies over some base space, some algebraic space. And for Calabi-Yau manifolds, this space is the moduli space of this deformation. This is kind of the deformation space of the manifold. So the base space has a meaning as a deformation space. While in these abstract variations of Hodge structure, I give you some rules how this HPQ is allowed to change along this general manifold. It's general algebraic space.
And the 4 was also.
And the 4 is completely irrelevant. Yeah, so the 4 is indeed completely irrelevant. Also, the Calabi-Yau condition is completely irrelevant for the finiteness. Yeah. Right. So the Calabi-Yau condition is, as you know, relevant for the unobstructedness of deformations, right? So there is some interplay between deformation theory and Calabi-Yauness, but indeed the theorem is not. It's not even restricted to geometry. So the PQ decomposition doesn't have to come from a Kähler manifold.
But the actual motivation came very specifically
Exactly.
from Cabio 4, right? So that was
Exactly. It came actually. So what happened is I came from this thinking about these asymptotic Hodge theory for other conjectures, and then I read the papers from Catani, Delin, Kaplan, and I found that this kind of seems to answer this long conjecture, and so I made contact with the mathematician and asked, can they extend it there? And then of course they are able to prove things. Yeah, so this is that's how this collaboration started.
Yeah. So, an example of such a Calabi-Yau fourfold. Tame mentioned Calabi-Yau 6. Yeah? So that means just a homogeneity equation of degree 6 and 7 variables. Yeah? So if I write down such an equation, so lots of coefficients, so I cannot even write it down. Yeah? So can you see various parts of your story in such a complete story of the coefficients?
You can see it, yes, but it's horribly complicated. So what you can do is you can take this sextic, you can compute the periods of the sextic. You have to compute it like the exact periods. So you need to really compute the whole. So you have to compute the Picard-Fuchs equation, and you have to solve Picard-Fuchs equation. You have to match kind of boundary conditions, and then this gives you a horribly complicated. For Calabi-Yau threefold, I know it is that these Myers functions and so on. And then you have to plug these functions into these equations, and then you have to try to solve them. And even a computer, so some of us are doing this, even a computer kind of fails. But what you know is that once you do it properly, you will find finitely many solutions on. So you can check it in all kinds of examples. I don't know if this is your question, but so the reason to understand the reason why this works, you cannot see an example, I would say. It's just It's just kind of this remarkably constrained behavior of your functions near the points where everything degenerates.
So I assume you cannot really actually write down the defining equations of any of these loci. I mean, you say that you can show it's definable, but
well, you can formally do it. So these are just the equations which I wrote down. But I agree with you. So what excites me very much is kind of understanding even the Catani-Delin-Kaplan theorem in this question which you are raising. Like, do it for an example and then if you solve this equation, there should be an algebraic equation coming out of this highly non-transcendental stuff. Right? So it's kind of a reduction of transcendental functions to this algebraic equation through the integrality. And I don't have a good feeling for this, but I want to see it. I understand the various steps in the proofs relatively well, but I don't have a good feeling why this is happening. Yeah, so indeed. It should be possible to do it, and it would be very nice to understand what are kind of the coefficients in this algebraic equation. What's the meaning of this? And what is also a very good question is, so what is the analog of the Hodge conjecture which comes from the self-dual classes? It would be very exciting.
So what do you mean by this?
So it would be very nice to know what is the, for the Hodge conjecture, you know the algebraicity. So your Hodge conjecture says that you have these integral classes on the, or not necessarily integral, but over Q on this manifold, and then you can associate algebraic cycles to it. Now we have these self-dual classes. What sort of cycles do we have to associate to them?
Right, because in your result, only the Hodge type was important.
Yeah.
Now you wonder what happens if
What happens geometrically? Now this is a algebraic geometry question which I don't know how to answer. There should be, so in string theory you can probably translate it into some question about debraying. But it would be very exciting to have a conjecture which is taking this into account. Then you can forget the Hodge theory part and just leave it the conjecture. It would be very cool.
But this feels more like because you're just looking at self-dual, right? So it's a bit like looking at harmonics and trying to see when they meet integral cohomology classes. Split them up into self-dual and self-duality when they go, when those can be represented.
Right, exactly. So for K3s and so on, this is understood to some extent. But what is the general geometric criterion which you should use there?
There's no like the Tame conjecture, like this. Is there a version for self-dual cohomology classes, or I don't know.
Are there more questions, or maybe people at home? People at home. Let's see.
Is anybody home?
Well, they are nominally here.
If you still want to turn your microphone on.
Okay, then if there's no more questions, yeah, let's thank Thomas again. Thanks a lot. All right. Thanks.
So is someone